Birds have been a source of inspiration to scientists and engineers for centuries in the form of applications to aircraft design or insights into bird flight. But the more that we look up at these wonderful birds, the more questions we actually have about them. And one of these open questions relates to the aerodynamic function of covert feathers.
In this study, we wanted to understand how the coverts affect the air around the wing. And we wanted to ask whether having multiple rows of coverts have any aerodynamic benefits. Rather than doing this on an actual bird, we did it on something we call a simplified engineering analogy. What you see here is a wing that's been really well characterized in the literature, and the coverts are modeled as these flaps that can passively deploy in response to the aerodynamic loads.
Now, even though all birds have these feathers, scientists and engineers thus far have only been able to quantify or measure their deployment during high angle of attack maneuvers. No study has been able to measure or quantify their actual aerodynamic function in flight.
To evaluate this analogy, we use the wind tunnel, and the wind tunnel can provide a very helpful facility for this experiment since they allow us to control the wind speed and wind conditions around the wing. We also can acquire a high-resolution force measurement using the 6-axis force torque transducer we have here, and this allows us to measure the lift and drag on the wing with and without the flaps.
And what we discovered is that the flaps improve aerodynamic performance using a variety of different flow physics. These physics depend on the flap's location on the wing surface. For example, if you place the flap towards the front of the wing, they improve aerodynamic performance by interacting with the separated flow shear layer. On the other hand, if you place the flap towards the rear of the wing, they also improve the aerodynamic performance, but by acting as a pressure dam, which prevents the propagation of high pressure in the wake towards the front of the wing.
And what we found was that the shear layer interaction flow control mechanism was additive, meaning as you add more and more of these flaps, the shear layer becomes more effective and the lift benefits add up, whereas the pressure dam effect was not additive. However, you can exploit both flow control mechanisms simultaneously, getting up to 50% lift improvement and 30% drag reduction.
Inspired by the findings in the wind tunnel, we wanted to see if the benefits of the covert flaps translated to flight. And so we installed these covert flaps on a remote-controlled model aircraft. 3 flaps on the top side of each wing in a position analogous to that of the bird feathers and matching the configuration that performed the best in the wind tunnel. To conduct our flight experiments, we designed an autonomous stall maneuver where the aircraft is commanded to slow down continuously while maintaining altitude. So it has to continue pitching up, reaching higher and higher angles of attack until ultimately the wings stall and the aircraft falls out of the sky. Covert flaps, when they deploy, enable the aircraft to reach higher angles of attack and effectively delay the stall.
These devices add minimal weight, have no complexity, requires no additional power or actuation, and yet can mitigate stall and allow airplanes to do maneuvers that would be extremely dangerous or even impossible to perform, making them especially attractive for the next generation of small-scale uncrewed aerial vehicles.